And I'll start sharing a screen here in a second.
Hi, sorry, can I ask a question?
Yes, you most certainly can.
Okay, I think I emailed you about this last night, but for 16D on week 2,
Yeah, I was looking at that. Was it 16B or 16D?
16D.
Because why was I'm going into my week
Because
2.
I was my instinct is saying that the answer key might be incorrect or I'm incorrect in my thinking.
No, it's all right. It's all right. 16D. So I'm looking at this and I only see 16. When I emailed you that response there yesterday,
Yeah.
what was it about the airplane?
No, it was about I'm in the wrong class.
Because motion problem set answer, and week 2 questions page 1.
Do I have here? Let me just look at
Because
it.
I'm going to screenshot. Where are we here now? And am I sharing? Okay, I'm sharing now. Okay, so this is week 2, and these are I've got A, B,
Sorry, 16C.
Okay, all right.
Sorry, I don't know why I thought it was C.
No problem. Yeah, it's like,
By
go
the time
ahead.
it reached 50 meters per second, but the answer is using the velocity found in B. So why would you use the velocity found in B if you're given velocity for C?
I'm just looking here. See, for this question here, during takeoff of an airplane goes from 0 to 50 in 8 seconds. So
Yes.
what is its acceleration? Okay. B, going back to the lab, there's kind of a relationship here. If something is going from standing to 50 meters per second, I'm actually giving you 2 bits of information. Okay. I'm giving you the fact that it started from 0, and I'm giving you its new velocity. All right. So when you see something is starting from 0, or from, I don't know how I would word it, but standing, then that means that it's starting from 0 and it's going to here. And what I can do is, I think I gave you A, B, and C answers there yesterday, didn't I?
No, you just gave me B, which is fine. I understand B. But I just, with C, I don't understand why it says by the time it reaches 50 meters per second. So it reaches 50 meters per second in 8 seconds.
Yeah.
So you're doing the distance.
So how far has it traveled? So the
but it's
go ahead.
To find the distance, the answer uses the 31.25 that you found in B, which I don't understand why you would do that when you have the velocity it reaches in the 8 seconds.
What I'll do is I'll modify the answer there that I sent to you. Like this, our lecture here today probably be an hour. It's kind of short. And what I'll do is, as soon the test will open at 3, and what I'll do is I'll send you guys a detailed answer, kind of like, I think I sent you like a massive one, didn't I? Or didn't I? I don't know.
You sent me
a good one.
Yeah, you sent me a good explanation.
And what I'm going to do is,
I just don't understand.
I'll take that information and I'll apply it.
Why you use the 31.25 when you're given 50 meters per second?
How fast is it? Now, is it? Yeah, that could be an issue. I'm looking at that there right now because, yeah, I can see that. What I'll do is I'll update that and I'll send it to everybody just to make sure. And it's all good. What I'll do, yeah, I've got that on my notes. I'll 16 A, B, and C. Nope, you guys are good. I'll send that out. No worries. Hey, great question. What else is going on? Anybody? Talk to me. Questions? Feel free to speak. Believe in yourselves, guys. You guys are doing great. You have your formula sheet there. pull out what I'm asking for, pull out what I've given you, and then you've got everything on a piece of paper. Mass, velocity 1, hey, whoa, this and that. Okay, looking for that. Find your formula. The numbers are there. The answers are there. It's A, B, C, D. It's there. So now, are all my tests going to be like this? No. This is kind of a take-home assignment test. The next one there, I think it's just there before reading week. We might make it, I might give you 24 hours to do this. Or I like to give some flexibility just because there are screaming kids around, which you might hear frequently in the next hour. And but I like to give some type of window of opportunity and not just the 3 hours. So keep your questions going. Believe in yourselves. And is this stuff really exciting? No. But is it necessary from where to in order for you to get to where you want to be? Absolutely. So don't be afraid of this stuff. You think you're the first person to take a physics course and hate it? No. But you need this to get where you're going. Focus. You guys can do this, and I believe in all of you guys. All right. So don't be afraid of this stuff. You've got your formula sheet. There was a squared missing on the week 3 formulas. It's been since updated, so you'll use the week 3 formula sheet there to complete the test. And then if I can give you some advice, get the test done sooner than later, because the stuff you've been doing, it's in there. You've been working on your homework. Get it done, get it out of the way, and then it's gone. And then we're on to the next section. All right? Don't let this slide there for a week and things kind of taper off, because the way these courses go, and especially online, like if I was in class there with you guys, I would be able to, lecture takes an hour and a half, and then we have an hour and a half of questions, this and that, and I could work through students who think they need extra help, and I can still do that. The medium has changed, but the message is still the same. Okay, you guys have to be vocal, and I can't read your minds, and if something is going on, you guys have to let me know, and preferably as early as possible, and keep me in the loop. So we're in this together. Let me know how you guys are doing. The test will open there this aft, and the assignment, as I said, will come out in a day or so, and no labs there this week. Lab 2 will come out there next week. So if you guys have any questions at all, let me know, and I think you guys will do just fine. All right. So if you guys got nothing, I got nothing. All right. You guys have everything you guys need. Okay. Get that test done. Do it well. And we're on to Unit 2. This is where we are. And some of this will look familiar. Like last week there, we were talking about free falling and these kinds of things. Parachuting out of an airplane. These kinds of things. By the way, just for like on the quiz, some people had inquired about why that, when you're falling out of an airplane, and I'm asking for, I don't know, say the distance or something, or, after 3 seconds, and you're thinking, hey, wait a second, you didn't give me any mass, you didn't give me anything else, all you gave me is that a dude is jumping out of an airplane, and 3 seconds later, and you're asking me to find this. Anything to do with all that kind of stuff, you know that there's a given. Gravity's always in there playing a force. Okay? And just remember your Newton's 3 forces, right? Or your Newton's 3 laws and how they interact. Oh, man, I don't feel good. Ugh. Too much hot sauce on my eggs there this morning. But anyway, you guys will do just fine. I'm not worried at all. Let's go. Gravity and gravitational forces. And by the way, thank you guys for coming. I know that you guys are probably almost overwhelmed, okay? But keep it going, stay focused, and all is well. Reading week is the week after next. So that's your catch-up time, and honestly, it's my catch-up time as well. Some of the things in this PowerPoint are going to, I don't know, blow your mind. And it's some of the stuff is really cool. Okay, albeit Star Trek cool. But yeah, it'll be all right. It'll be all right. Here we're getting into gravity and gravitational forces. What do we got here? Newton and the apple. We've gone over this already. Newton first started thinking about gravity after being hit in the head with an apple. And it was shortly after this that he realized that gravity must extend beyond the Earth's surface, right? Because the apple's up there. Well, the apple fell on my head, so that must mean even though I have a pen here and it falls to the ground, well, gravity still exists up there at the top of the apple tree. So something's going on here. Gravity extends from the ground up to somewhere. Okay? He was the first person to realize that it was this force that kept the moon in orbit around the Earth. And you look at... I'll just keep going. And for the next 20 years, he studied the sun, moon, the planets, and eventually led to this publication that basically changed the entire way we think. And the law...
I'm just in physics right now, but I had my lawyer this morning.
Hi. You might want to turn off your microphone.
Yeah.
It's all okay.
I know. It's like literally physics.
Hi. Can everyone turn off their microphone, please? Thank you.
It doesn't even seem to matter what kind of stove you use.
Kelly, I think you're here. I think we can hear you. Thank you. Very good. This is where it's going to get maybe new. Like gravity. What is it? Okay, as far as we can see here on Earth, you know, I have a pen and it drops. And it does it every single time. But what is causing this? And the crazy thing is yes, the Earth has gravity. And it's this force that pulls things, all things, towards its core, towards its center. That's what gravity is. And would you believe that you have gravity? This can of Diet Coke has gravity in it that is acting on this pen. This pen has gravity, and it's exerting a force, a pulling force. Everything that has mass has gravity. And we'll get into more of these, and I just want to kind of explain this here. And we're going to start slow, but once this clicks, it's not really that bad. I think there's only 2 formulas there for this week anyway. Okay. There we go. Okay. 2 formulas there and 1 constant. That's all there is there for this week. Okay. Basically, what we're talking about here is the greater the mass, the greater the force of attraction. So gravity is dependent upon mass, the amount of atoms that are in something. And you think about this can of Coke here. Okay, if what I'm saying is true, then this thing has an attractive force on all things, but its mass is very small. You look at the mass of the Earth, it's enormous. Can you imagine the force of gravity on everything? Well, we don't have to imagine. That's it. So basically, the greater the mass, the stronger the attractive force. And inversely, point number 2, the greater the distance between the two. Okay, the weaker the force gets. So the bigger the mass, the bigger the gravity. The farther apart two objects are, the weaker the gravity. That's how this thing works. Kind of makes sense, right? Maybe not, but we'll get in there. The universal gravitational constant. And you've got force is equal to G, mass 1, mass 2, distance squared. Okay? So the force of gravity between two objects is found by multiplying their masses and dividing by the square of the distance and multiplying by G. So this is a formula here that we can kind of use. We can use this with a can of Coke and a pencil, which I'll show you. We can use this there between Jupiter and Saturn. And all these kinds of, like, this is a really good formula here. Mass 1 is going to be the mass of one object. Mass 2 is going to be the mass of the other object. Distance, okay, and G, you always have G. G is that number there at the bottom of your screen. The magnitude of G is identical to the magnitude of the force between a pair of objects that are 1 kilogram and 1 kilogram in size, and they're 1 meter apart. So you see here, if I have a 1 kg object and another kg object 1 meter apart, they are exerting an attractive force on each other. This silly number here, 6.67 times 10 to the negative 11 Newton meter squared kg squared per kg squared. And you just look at that number. It's a ridiculously small number. So let's say this can of Coke is a kg. Let's say this calculator is a kg. All right. They're both exhibiting this force on each other, which is pretty negligible. You know, you're not going to move mountains with that force. But there is a force there. So anything that has mass will have gravity. And you can guys go on YouTube, and I'm recording this, so you guys can go back if you don't get a chance to write this down. But when you're talking these monumental objects there in space, like the sun, and the sun is actually kind of a medium-sized star. You can get into massive suns, you know what I mean, that are 100 times the size of our sun. So here we're just talking incredible amount of mass. So meaning that because there's all this mass, you're going to have an incredible amount of gravitational pull on other interstellar bodies all over the place. And if you looking straight ahead and you can see a star out in the horizon, but what they've done now is maybe a sun closer to you than the star gets in the way of the star. So you can't see the star because the star behind it, this light is coming, but it can't get through the sun. What will happen is the gravity on this sun is so strong that what it'll actually do is it'll bend the light coming from the star behind it around it. And you can actually see these, gravity can actually bend light. And if you look at a black hole, you know what I mean? There you're talking the ultimate gravity, where nothing escapes. And really good book. Stephen Hawking's, he passed away, was it last year or the year before? One of the greatest theoretical physicists of our time. He later came out and said that the book, A Brief History in Time, wasn't as good as it could have been. But you guys want to read about black holes and these kinds of things, gravity and force and all these things that go on outside of our immediate environment. It's a really good book. It's you can get it for $1 at a used bookstore now. It's about this big, and it's not too bad. It's a good little book. But anyway, force is equal to gravity times mass divided by the distance squared. There's your G. Okay. This value for G indicates that the force of gravity is a pretty weak force, as we just said. As a result, we sense gravity only when masses similar to that of the Earth are involved. So I know that can of Coca-Cola is exerting a force on me, and I'm actually exerting, the same force back at it. All right, but our masses are so small that the gravity is negligible. All right, but when you're talking about massive masses, that's where the gravity, you start to see the effects. Have a look here. Law of the universal gravitation and Newton's third law. Newton's third law. For every action, there's an opposite and equal reaction, right? If you have a look here, I'm reading right here. So, if the Earth is pushing you down with gravity, right here, so the Earth is pushing us down because of its gravity. But Newton's third law says that there's an opposite and equal reaction. So, aren't you pulling up with a force equal but opposite? All right. The gravity is pushing you down, and you are pushing yourself up. And it is true. Even when you walk on the floor, the floor is pushing back at you. There's always this opposite and equal reaction. So you move more than the Earth because the Earth is much more massive than you are. So the Earth is exhibiting a force on you, and you are exhibiting a force on the Earth. But you see there that the mass of the Earth is so much more than us, so we're the ones that show movement. That pen right there is exerting a force on Earth, but the Earth just kind of laughs at it. Okay, and the Earth doesn't move. The pen is so small that that's the only thing that we see. But there are two things happening here. Okay? A force from gravity and you pushing back on it. So therefore now we can stand up and withhold and safeguard against gravity, kind of a thing. Okay? This is more about the bottom of the equation there. We were the first half of the equation, we were talking about the bigger the masses, the bigger the gravity. Underneath it, though, we talk about distance. And the farther you are away from a gravitational body of whatever sorts, the weaker the force is going to be. Understandably. And I found this there. If you could stand on a tower 4,000 miles away, American, you would weigh 1/4 your usual weight. And you have to see here, I tried to, I don't know if you guys can see this or not in here. So let's say I'm 160 pounds, I wish, on the surface of the Earth. And how far away are we from the center of the Earth, which is the radius of the Earth? Okay, so we're one radius away from the center of the Earth. And I weigh 160 pounds. Okay, if you double that, so now this is 4,000 miles. Okay, if I stand on the top of up here, so now I'm 8,000 miles from the center of the Earth, which is 2 radius. Look at my weight there. It's gone down by 1/4, or gone down to 1/4. So there is a relationship here. If you 2 times farther, it's 2 squared. 1/2 squared. If you're 3 times farther, you'll be 1/9. 3 squared. The gravitational pull. We'll get into, I'm just throwing things at you and it'll all be clear in a little bit. Okay. So, we call this there the inverse square law. And it's used actually all over the place when we're talking about distance and gravitational forces, even there when we talk about light. And we'll get there. The space surrounding all objects with mass is energized with a gravitational field. Okay, so here we're just talking about everything is exerting a gravitational field on everything else, okay? But this gravitational field weakens as you increase the distance. So right here, look at these guys, all right? They're as close as they're ever going to get. They're exerting their gravitational forces on each other, and they're at their strongest. But as we start to move things apart, the ability of this guy here to pull on this guy here is weakening, 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 weakening. And it all works by this. If you double the length, you 1/4 the strength. If you triple the length, you 1/9 the strength. But we'll show you guys this. This is a really good example here that please have a look at this, because you might see a question like this there later on. Okay, just the whole idea of spreading light out, and the light works in the same way, goes out and it starts to scatter. And watch this video. It's really, really, really good. Don't get confused by the center part. But look at the beginning and look at the end, and watch the video there in its totality, and it should make some good sense with what we're talking about here. So what we're the formula for the inverse square law is this one right here, and where the force of gravity is dependent upon the distance. And if you double the distance, you 1/4 the gravitational field. So we can see there, if you watch that video, we can see there that the brightness of the light rays decreases as the square of the distance increases. So if you watch the video there, they're talking about light and it scatters. And it's just like shining a flashlight into the woods at night. The farther it gets, the weaker the light gets. And this is what we're talking about here. The same thing there with gravitational pull. The farther the two bodies go from each other, the weaker the pull is. What do we got here? So just to show you guys some examples. An object on Earth's surface weighs 1 Newton. Okay? If we move it twice the distance from the Earth's center, what's going to happen? Gravity now is going to be 1/4. Okay, so it'll weigh 1/4 Newton. If we move it 3 times the distance, so here's one radius, so it's sitting on the Earth's surface. Here's another one, so I'm 2 times. And then here's another one. So now I'm 3 times the radius. And you see here, 1/d squared, 3 times, 3 squared is 9. So now the force of gravity is 1/9. So that's how this one goes. This is called the inverse square law. So this is what we got here. All right. Now, test yourself. I put the 2 formulas here there for this week, and we're just going to go through these. Like a lot of these are, like there's some simple math, but again, it's not bad math. It's just plug and play. Let your calculator and your formula sheet be the donkey, be the beast of burden. Okay? Because you don't know what the next question is going to be, so you treat every question like a new one. Okay, what's he asking for? Write it down. What's he giving me? Write that down. And then you take your ingredients there that I've given you and find the formula there that you need, right? So let's have a look here. According to the formula for gravitational force, what happens to the force between 2 bodies if the mass of one of the bodies is doubled? Well, have a look here. Let's say we just double the mass of M1. What's going to happen to this number? There's your numerator, there's your denominator of the fraction there. If you double the mass of M1, therefore now you're increasing your numerator, you're making the number bigger. So if you increase the mass, you're increasing the force. So the stronger the mass, the bigger the mass, and in this case here, doubling of the mass, You're going to double the force. Number 2, what happens if both masses are doubled? So I'm doubling M1 and I'm doubling M2. The same principle there. I'm actually going to quadruple the force. All right. What is the magnitude of the gravitational force between two 1 kilogram bodies that are 1 meter apart? And this is the gravitational constant. Okay, it's missing some units there, but it's there. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And kg squared. Good. So what do we have here now? What do we have here? You see here, if I put in question here, between two masses, 1 kg and 1 kg. Well, here, 1 kg, 1 kg, square, square, and the distance is 1 meter apart. Therefore, this whole thing just goes to 1, and all you're left with is this number here. So this number here is a constant at these parameters, 1 kg and 1 meter apart. Let's do a real question here. What is the force of gravity between two objects with masses of 10 kg and 40 kg that are separated by 1,000 meters? Plug and play. So what am I looking for? Force of gravity. Okay, I have this formula here. All right. He's giving me mass and mass. Well, I have mass 1 and mass 2 separated by 1,000 meters distance. Plug and play. Now, hopefully there you guys have access there to a scientific calculator. We'll definitely need it there this week in chemistry if you're in my chemistry course. And now this is where we start to use our scientific calculator. So when you get these weird, insanely small numbers or insanely massive numbers, this is where you need to have scientific calculator here. So you plug, here's your formula, plug your numbers in. Please do not plug in the whole thing into your calculator at once with all the brackets, times 10 to the times 40, all divided. You'll get a wrong answer. Do it in steps. Like, what are some things there that we can clean up? Well, you've got 1,000 squared. Get rid of 1,000 squared, turn it into a mil. Okay, so now you have, and then 10 times 40 is 400 divided by a million. We'll clean that up into one number, whatever that works out to be. And then at the very end, multiply this number. And if we haven't dealt with this stuff here, let me show you. Let's have a look here. I'm just going to try something out. I don't want you guys to make any mistakes on this. So if you look at this, good. Now, times 6.02 times 10 to the 5. Something like this. And let's go to here. What's my answer? How do I plug this in to my calculator so that I have a decent answer? Well, this is, and it all is the EXP button on here. All right. Please don't use the Y to the X button on your calculator, because then you'll need brackets and all these kinds of things. And the more fooling around with your calculator, the more ability there is to make a mistake. All right. So how do you input this into the calculator? 6.67 EXP button. I'll just go with that. Okay, negative 11 times 6.02 EXP. Okay, to the 5, and then hit equals. I have no idea what that number is, but if you guys have any issues with this, get a hold of me ASAP. I'm around all afternoon, so email me, bother me, hassle me. I love it. okay? Because you will have to do this for this course and chemistry as well. And I don't want to make mistakes, but don't make calculator mistakes, okay? So I can fix this quick as a bunny if you guys have any issues. So this is where we're at for that one. So we just go back to this one here. What did I ask you? Force of gravity. Gave you the numbers. You plug and play. So two objects separated by 1,000 meters. One 10 kilogram, the other 40. This is the force that they're exerting on each other. Number 5. Calculate the gravitational force between two friends who are 2 meters apart and have masses of 70 kg and 80 kg. Plug and play. Okay. Number 6, but how much does the gravitational field between two objects decrease when the distance between their center is doubled? Well, if it's doubled, then the gravitational force goes to 1/4. If the distance is tripled, gravitational force goes to 1/9. If you increase it by 10, so it's 10 times the distance of what it was before, the gravitational force is 1/10 squared, which is 1/100. All right. 7. Consider an apple on the top of an apple tree that is pulled by the Earth's gravity with a force of 1 Newton. If the apple were if the tree was twice as tall, would the gravitational field be only 1/4 as strong? No. So what the question is asking, if I double the size of the apple tree, am I decreasing the gravitational force by a factor of 1/4? No. That whole ideology is dealing with radial distance. So if you remember the radius of the Earth, right? We're on top of it. The center of the Earth is in the center. Yes. So that distance is the radius. We weigh this much, 1 radial distance. All right. Sorry, I got my hand here. You can't really see it. If I double the radial distance, now that rule works. And what rule I'm talking about? This one right here. Okay. So my answer is no. Only the tree is twice as tall, but the distance to the center of the Earth is basically the same. You only went up another tree distance. And think radial distances in order for this formula to come into effect. How does the gravitational field of a planet vary with distance an object travels from the planet? So like we're going to get into satellites. And we send a satellite away from the Earth and it's flying away at the Earth. What is happening here? The Earth is trying to keep that satellite here. And that's why you need so much fuel in a rocket to break the Earth's gravitational field, right? Massive amounts of liquid hydrogen. The gravitational field will decrease according to the inverse square law. For every planet radius, an object moves away from the planet. So every planet radius, now the inverse square law can take effect. And these answers here are pretty in-depth. You know, I'm just looking for some type of comprehension here. So how does the gravitational field of a planet vary as an object is going? Every radial distance, the gravitational field is cut in half. Number 9, where do you weigh more, at sea level or at the top of Mount Everest? Interesting. Our mass is the same at sea level and at the top of Mount Everest, but our weight is a lot less. At sea level, you weigh a lot more because you are closer to the center of the Earth. There's more gravity there than there is at the top of Mount Everest. Interesting note, completely sidetracked, but something to Google. Water boils at 100 degrees Celsius, right? You know, what temperature does water boil on the top of Everest? Completely unrelated, don't do it now, but interesting to know. The birth of planets and stars. Okay? You have to think there that billions of years ago, you know, Earth was just a ball of a cloud of dust. Billions and billions and billions of years ago. And how do planets form? How do stars form? All planets, all stars are round. So at any given point on the surface of the sun, it's always equidistant to the center. Radius extends out in all directions for a sun, and this kind of gives us an idea of how they were formed. We know that everything attracts everything else, so that all parts of the Earth they have attractive. They've all everything has attracted together. So that eventually, at one point in time, billions and billions and billions of years ago, there was just maybe a grain of sand here, and then another grain of sand out in space. They came together, and you see now, 2 grains of sand have twice the gravity as 1 grain of sand. So they got more pull. And then another one comes in because the force of attraction, its gravity is stronger than anything else currently in the nearest 100 billion kilometers because you're out in space. And now, you see now, and eventually maybe a year from now, you've got half a kilogram of sand that is all kind of together now with its own kind of attractive force. And as billions of years come, an entire planet can be born, or star, from this method. That's what we think anyway. Since everything pulls on everything else, then the planets must pull on each other as well. And they do. Okay? They do. The sun is the big boss here. But planets in their rotation can come in kind of close proximity to each other, and they create these little wobbles in each other, and because they're exerting gravitational force on each other. And these wobbles are called perturbations. All right. When Jupiter orbits near Saturn, the pull from Saturn on Jupiter increases slightly because the distance has been reduced. Like these orbits, sometimes the planets kind of come, not saying in close contact, but closer contact, that there's this gravitational interaction. And when these planets come closer together than normal, it causes these wobbling effect. And these wobbles are known as perturbations. Okay, and we can measure them and predict them, and they're there. It was the study of these perturbations in the orbit of Uranus in 1840 that led astronomers to the discovery of Neptune. Then again in 1930 to the discovery of Pluto. So we didn't even know that these planets existed until we saw these wobblings. So why is Uranus wobbling? That must mean that there is something out there exerting a force on it. And I don't know if you guys have ever heard of Planet X. They think that there's a planet out there beyond Pluto, but we just can't find it. And there's something out there that is causing wobbling on the other planets. And they don't know where that's why there's this theory on Planet X. I think it's called maybe Planet 9. Maybe Planet 10, something like that. It's a planet out there that we don't know. And Pluto, you see these perturbations here. Pluto used to be a planet. It's not a planet anymore. They call it a dwarf planet because these perturbations on Pluto led to the discovery of other orbiting bodies that are basically the same size as Pluto. So why is Pluto a planet and these ones aren't? So they had to downgrade Pluto there to a dwarf planet. Okay. That's it for that. Gravitational pull. So the only formula, there's 2 formulas there, is these guys here. Okay? Not too bad, not too bad. And we'll go over the questions there at the that I've included. Now we're on to projectile motion. And projectile motion, we've looked at it. I think it was week 2, we were talking about throwing a football, right? You've got 2 components to this. And Johnny throws the football And it actually moves in two directions when you throw it. There is the vertical rise and fall, the up and down. It's going up, and then it reaches a maximum, and then it starts to come down again. And that's what this green thing is. And there's a really, really cool video that I am going to play, I think, during here. I want you guys to see. But there is also here this horizontal movement. There's two things happening, and they are absolutely independent of each other. And I'm going to show you this, all right? Projectile is an object that moves through the air or through space under the influence of gravity. Now, if you go back here, which one is, I don't know what's the word I'm looking for, prone to gravity? Which one here is going to follow gravity? Here's your vertical. It's going up, it's fighting gravity, and then, no, can't beat it. There, I'm back down again. This horizontal movement, though, is immune. It's just a force that goes across. And I'll show you this. It may not make sense, but I'll show you. Without gravity, you could toss a rock skyward and it would follow a straight line path. Of course it would, because if there's no gravity, the rock is just going to go out into space. The study of this parabolic path, parabola, it's an upside down parabola, all right, can be made much simpler when we examine the projectile's horizontal and vertical paths separately. So let's have a look. The horizontal component. Okay, so I'm throwing the football from me to Tim over there. He's 20 meters away. Similar to that of a bowling ball rolling freely without any force of friction. You think about that. What is impeding that football going from me? We're not talking about the up and down. We're only talking about left to right or forward straight. Basically, you're only talking about wind resistance, but, you know, on a nice day, there isn't any, right? So the object will fly with a constant straight line velocity. It flies with its own inertia. Should make sense. Inertia. The ability or tendency of an object to remain at rest or remain at a constant speed. All right? Flies with its own inertia, covering equal distance in equal time periods. So it just goes. It's the vertical component now, all right, similar to that of an object in free fall. Aha. So here we've got gravity involved now. The object will accelerate, covering greater distances in each successive time period. So something's going on here. There's an acceleration involved. You think, what is going on right here at this point? It's going up, 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 and then for a millionth of a second, it's just sitting there. And then it comes back down. It's almost like somebody dropped it out of an airplane. I'll show you. So the resulting parabolic path is a combination of these two motions. So you have the vertical and horizontal. So what we've got here now, this is the projectile motion. And this going back to myself throwing a football. And you have to see here, here's your force, velocity, it's going up here. And you see here, we've actually got vectors indicating what forces are happening on this. And let's just break this down. Let's look at the horizontal component. Okay, here it's here. Hey, it doesn't really look like it's really changed much. Look at the arrow. It's this long, still this long. Look at this arrow. And you see it really, the horizontal component doesn't really change much at all. It's still moving forward, same magnitude, it's moving and shaking the way it should be. Let's look at the vertical component though. So I'm throwing the football up, lots of gusto there. And now it's fighting gravity now. And then eventually, hey, wait a second. There isn't any force acting on this up. Where's my acceleration? What's going on? Because there is none. It's exhausted it. At this point in time, gravity is equal to the force there that was thrown by me. So therefore now there is no force. There is no acceleration vertically. So that's why there's only one vector here. And it's that same vector moving left, right, horizontal. That's all there is. And then you go along here, it's starting to come down. The same force is still pushing it forward, but now gravity is pushing it down. And you'll see here, the farther it falls, the more force that's going on because of acceleration from a free fall. I am going to show this because I want you guys to see this. This is crazy important. And let's have a look here. What silly commercial do they have? Oh, they don't have any. Okay, good. So this guy's got some billiard balls that he's drilled a hole in. And he's got this one here and another one. So one ball is going to fly out. The other ball is just going to drop. So, and you'll see there, this ball basically just dropped. So it was like free falling out of an airplane. This ball here was pushed. Okay, so it's got a left-right component. But it also has, even though something is moving like a football, a projectile, it's getting pushed, gravity is still acting on it like it's in free fall. And you'll see there that even though this ball here was pushed and this ball here wasn't pushed, they still hit the ground at the same time because the horizontal component acts differently than the vertical component. And what do we got here now? No, this is what we're looking at. So just going back there to this one here, the ball that was pushed out. Okay, there's your force. It's pushing, pushing, pushing. But if you negate that, it still hit the same time on the ground as something that just fell, like you just kind of bloop, dropped it. So we know there that these forces act independently of each other. Even though this one's getting pushed, it's really just free falling. So when you throw a football, yes, it has the force propelling it to Tim 20 meters away, but if you at the top of your football arch where the ball comes up and then now it's going to Tim, if you were standing there at a ladder watching that football go by you towards Tim and you had another football and you just dropped it, they would both hit the ground, or both, by the time Tim caught it, it would hit the ground as well. Satellites there, they're just simply fast-moving projectiles. We're almost done here, guys. I purposely made this there only about an hour or so because I know you guys have bigger fish to fry there today. But yeah, we should be done in about 5 minutes or 10 minutes. And if you guys have any questions, we can talk about those there. But remember, if an object is launched horizontally to the Earth in the absence of gravity, so if we just launch a rocket horizontally, like towards the horizon, eventually, it's going to go off out into space. It's gravity that makes objects fall. Okay? And if we launch a rocket there horizontally towards the horizon, gravity is going to make it come back down. But an Earth satellite is a projectile, it's going to be weird to say this, that falls around the Earth and not into it. The speed of a satellite must be great enough to ensure that its falling distance matches the curvature of the Earth. It's all about speed. If you got a ball on a string, because that's what's happening. Remember that centrifugal force, right? And you have this ball on the string. And the only reason this ball is flying around is because of the speed. That's why satellites, man, are moving mucho bueno fast. Okay? They're moving crazy fast. Because the minute they stop moving fast, what happens to the ball? It falls down. And so if these satellites stop moving at the speed they are, they'll just crash right into Earth. So that's why they're moving. They're constantly, and I mean they're moving fast. All right? What do we got here? And this is just kind of the same thing. This is like the ball and the string. Let's say I'm in the middle. This is my string. Here's the ball. And it's flying. You remember your centrifugal force? All right. And these guys here are moving super fast, which keeps them in orbit. But if they stop moving super fast, then they'll just fall into the Earth. Basically the same thing. The Earth's surface drops vertically a distance of 5 meters for every 8,000 meters of horizontal distance. If an object could be launched fast enough horizontally, it would follow the Earth's curvature. And you have a look here. You've got to break that. You've got to, you know, the whole idea of falling into the Earth. That's why you need, like a rocket, needs so much fuel to break the Earth's gravitational field and to get out here. And as long as it keeps moving, it'll stay out here. But the minute there it slows down, it'll just crash right into Earth. There's a video there. I'm just trying to think of... hopefully there you guys can hear that.
It's important to keep satellites in orbit. Well, I guess not just important, it's crucial. It's what keeps a satellite in orbit. If we didn't have gravity, a satellite wouldn't orbit the Earth. It would just go flying off into space. What is gravity? The simple answer is the old one that Isaac Newton came up with. Gravity is a force that's an attraction between anything that's got mass. So I have mass, you have mass, the Earth has mass. All of that mass attracts other mass.
So gravity is a fundamental force. You wouldn't have orbiting satellites or the moon orbiting the Earth or the Earth orbiting the sun without gravity. When we hear the story about Newton and the apple falling off the tree onto his head, Newton was clever enough to work out that the Earth attracted the apple towards the Earth, but the apple also had a force pulling the Earth towards the apple. Now, because the mass of the Earth is so much bigger than the apple, you can't actually see the effect or measure the effect of the Earth moving towards the apple, but there is a opposite and equal forces pulling the apple and the Earth towards each other.
Another way you can think about it is if you tied a tennis ball to the end of a string and swing the tennis ball around over your head. The string is like gravity, and if you let go of the string, well, the tennis ball isn't held by a force spinning around you anymore. It just flies off in a straight line. In the same way, if we had a satellite going around the Earth and for whatever reason the Earth's gravity switched off, the satellite would just shoot off into space.
Perfect. And now we're on to the last couple slides here. So what is a projectile? A projectile is an object that travels through the air or through space under the influence of gravity. At the instant a cannon fires a cannonball horizontally over a level range, another cannonball held at the side of the cannon is released and dropped to the ground. So it's exactly the same thing as the two snooker balls or pool balls. One's flying, one is just dropped. Which is gonna hit the ground first? They both hit the ground at the same time. And it's just kind of a weird thing. This one here was shot out. This one here was just dropped. Okay, this one here is going to travel a lot farther horizontally, but they'll both hit the ground at the same time. Okay? A baseball is batted at an angle into the air. Once the ball is airborne and reaches its maximum height, ignoring air resistance, what is the ball's acceleration vertically and horizontally? Well, vertically, all we have is gravity. Okay? Remember that component? Even though you're firing the cannonball, and then this cannonball you're just dropping, gravity is affecting them both the same way. Horizontally, there is no, and as we stated there before, there's without wind or air resistance, but there's no force being exerted there on the ball left to right horizontally, 0 meters per second. Okay. Why does the vertical component of velocity for a projectile change with time, while the horizontal component of velocity does not? So going back here to this one, you'll see there that the horizontal component is all the same. No changey. But the vertical component is constantly changing because of gravity, right? Okay? And the vertical component of velocity for a projectile acts upon the force of gravity and therefore experiences acceleration down. The horizontal component has no net force acting on it, other than wind, and therefore travels at a constant straight line. And you can see there now, hopefully you guys are at a point, and I know you guys are, that some of these words here are starting to make sense. Like the horizontal component has no net force on it. All right? And if there's no net force, there's no acceleration. All right? But the vertical component has gravity on it, pushing it. So there's acceleration being exerted on this vertically, vertically, right from the get-go and all the way until Tim catches the ball. A stone is thrown upward at an angle. What happens to the horizontal component of its velocity as it rises and falls? So here, a stone is thrown up in the air. What's going on with this horizontal component? Nothing. The horizontal component doesn't change. There's no forces acting on it. Nothing. The thing is just going to go in a straight line. Go. Last question here, and this is the last slide. A stone is thrown upward at an angle. What happened here as it rises and falls? Oh, sorry, yeah. I haven't been feeling well there the past 12 hours. I don't know. Don't know what's going on. Maybe I need some Tylenol. A stone is thrown upward on an angle. What happens to the vertical component? And I put this in here just to show you there that the vertical component is completely at the mercy of gravity. That's how this one works, okay? That's about an hour. That's what I wanted. I know you guys have bigger and better things there to do there today. I'm going to be around here. What questions there do you guys have? What's going on? Talk to me. Is anything bothering you? I'm going to update 16 ABC on the week 2, and I'll send out an announcement there for that. But other than that, your exam will open there this afternoon, and I don't really anticipate any issues. You guys will have lots of time to fiddle around with it, get it going. But talk to me. Any questions? I think you guys are pretty good. Yeah. If you guys got nothing, I got nothing. Your test will open up there in an hour or two, so get cracking and do some reviewing. And I think it opens up at 3. And you guys will have the week. I think it's due there before class there next Tuesday. Okay. Other than that, I got nothing. Talk to me. If not, have a great day. Hello? Anybody? Thank you, guys. Joanna, assignment based. Yeah, the assignment is not based on this week. So, some advice, get your test done as soon as you can. You have a week to do it, all right? But get that out of the way because it's in there. You guys have been doing this there for 3 weeks, all right? Today's lecture is not on there. That's on next test, all right? So get that test done. The assignment is on the next unit. Today's stuff and next week and the week after, that kind of thing, all right? So don't do the assignment now. First thing, get that test done. That's all right, Joanna. You're going to do great. All of you guys are going to do great. Believe in yourselves. And if something isn't making sense, email me. I don't know how much I can do there with the test stuff, but you guys are going to be just fine. Just believe in yourself. Find the right formula for the information there that I gave you. Nothing more, nothing less. All right? And you guys just keep at it, man. You guys are going to do just fine. Bye, guys. Thanks, Austin. Bye, guys. You guys have any questions? Going once? Going twice? That's it. Thanks, Kelly. Have a great day. I'm just going to, at some point in time,